functions, okay? And before I really get into it, I just want to make sure that you remember the mantra for logarithms is always that a logarithm is just an exponent. So repeat that to yourself many, many times. It's going to help you get through a lot of these examples, a lot of the IXL links, a lot of the practice. A logarithm is an exponent. That's it. That's all you got to tell yourself. From there, everything will be fine, I promise. So if you're looking at the reason that kind of logarithms exist and why we use them so much in pre-calculus and algebra 2 is one of the main examples is the Richter scale, or how we measure the magnitude of earthquakes. Okay, so this idea where this x is in the exponent, all right, represents the difference in magnitudes on the Richter scale. Now, what's interesting about this, or how we can move forward with the mathematics, is that when we look at that curve, right, if we were trying to solve this for a magnitude or an output of 500, we would have to use the graph, and then we would kind of estimate something, a little bit after 2.5, so maybe 2.6, 2.7, right, something like that. So the idea is there has to be a way that we can solve exactly for x, all right, and that introduces this idea of logarithm, all right. So this base b logarithm of a number is the, as I said, exponent, right? The logarithm is just the exponent by which we must raise b to get that number. So that's kind of the whole point of doing this, and I'll fill in these other blanks to show you why. All right, so this exponential function is 1-to-1. All right, so its inverse is also a function. All right, and the inverse of an exponential function is the logarithmic function. All right, so whenever you're talking about exponential functions in any math class, you're most likely in the same unit or soon after, you're going to be also talking about logarithms. All right, they just go hand in hand because they're inverses of one another. Okay, so I'll just go kind of the way that I think of this. I'll rewrite it again. So log base b, so think of that as like a little subscript back to the normal, regular script of x equals y. All right, so I read this as log base b of x equals y. Okay, so this is how you read a logarithm. And then remember, when I want to go the other way and write it as an exponential equation, all right, I always teach students, and this can work for you or not, just to think of the word swoop. All right, so I go base b raised to the power of x, of y equals x. Let me do that again. Base b, do it again. Base b raised to the power of y equals x. You write it as b, base b raised to the power of y equals x. All right, so these right here, they mean the same thing. That's what kind of gets students a little bit confused, is that what I just highlighted in yellow, they are the same thing, just in different forms. So one is called logarithmic form, and the other is called exponential form. So you'll get used to kind of going back and forth between the two of those, okay? One quick note about logarithms, you can never take the logarithm of a negative number, right? The idea is if I have my bases always have to be positive, so I just make up a base, let's say 2, all right? So 2, log base 2 of, I'll just put x, equals a negative 6, all right? No, let me do this, sorry. Log base 2 of negative 6 equals, I'll just put x, all right? So if I swoop, that's 2 to the power of x equals negative 6. Now, here's the reason why this will never be the case, all right? Because whatever I choose for the power, whether that's a positive number, whether that's a fraction, whether it's a negative number, I'll never get a negative number in the output, right? If I use a negative exponent for x, I'll get a fraction, right? 1 over 2 to some power, all right? So I'll get probably a smaller number, all right? If I use a negative number, or a fraction, then I'll probably end up using like a radical. So that's how you get smaller numbers, but there's no way to get this negative in front of it. So that's why whenever you see a negative in this argument, so log base 2, whatever the base is, of a negative number, you know that it's going to be undefined. And I'll show you that later on in an example. Okay, so let's write these logarithms in exponential form. So let's practice, all right? So this is 1a. You always start with a base, and you're going to swoop. So 6, all right, base of 6 raised to the 1/2 power equals the square root of 6. All right, so if you need to swoop, 6 to the 1/2 power equals the square root of 6. That's how I swoop there. Let's do 2b. All right, 3 to the 2nd power equals 9. 3 raised to the 2nd power equals 9. All right, so always start at your base when you're doing this. Let's try these over here. Same idea. All right, 10 to the 6th power equals 1 million. 10 to the 6th power equals 1 million. Let's do the next one. 5 raised to the 2nd power equals 25. 5 to the 2nd power equals 25. Now, you may not know some of these, but I think you're pretty confident that 5 squared is 25, 3 squared is 9. So I always tell students, after you do this, just take a moment and does it actually, is it true? Is that a true statement that you just wrote? Okay, let's go the other way. This is what I see students having more trouble with, the going from logarithms to exponential form, just because they kind of forget where to put stuff in logs. So I'll try to help your brain out here. First, obviously, you're going to have a log. So write log log. Then I tell students it needs a base. All right, so the base is always going to be that big number there. So it's weird because it's a regular size number in the exponential equation, but it's actually a subscript, so kind of a smaller number in your logarithm. So log base 2 of 8 equals 3. And I always fall back on a logarithm is an exponent. So if you look at the answer here, right after the equal sign, it's equal to 3, and that 3 is the exponent. So the logarithm should always equal the exponent. And if you ever are like, man, I don't know if that's right, you can always go back and swoop, right? So 2 to the 3rd power equals 8. 2 to the 3rd power is equal to 8. Is that what I have right there? Yes. You don't have to do that. I'm just showing you that you can always confirm, before you move on. Okay, 2b, log base 5 of 25 equals 2. Try to practice this. I know it's tough without lines, but try to practice this as your log, your argument, and your exponent, which is after the equal sign, should all be written normally on the line, and your base should be a subscript a little bit smaller and below. All right, so that's log base 5 of 25 equals 2. Let's try 3c. All right, so we have log. All right, now watch this. This has a base of 10 in 3c. And whenever you do a base 10 logarithm, we'll do this in a moment, they're called common logarithms. So if you look at your phone calculator or any calculator and you just hit the word log, that's assuming a base of 10. And you never need to write it. So if you want to write the base of 10, you can, but I'm not going to write the base of 10. So log of 1 over 10,000 equals my exponent of -4. All right, so again, if you want that 10 in the base, go for it. I'm never going to write that because it's always assumed to be 10 if you don't write a base for the log. So log base 3 of 9 equals 2. Remember to swoop, change it to exponential form if you want to check it. So 3 squared equals 9. That's confirmed. Let's do 2b. Log base 5 of 125 equals 3. So 5 cubed equals 125. Excellent. The last one, 3c. Log base 2 of 1/2. That's kind of a tough one to do there because that's a regular fraction. Try again. Of 1/2 equals the exponent of -1. All right? Okay. Let's keep going. All right, so evaluating logarithms mentally. I'm going to obviously give you an opportunity to use Desmos to help you, but a lot of these you can do, especially the simple ones. A lot of these you'll be able to do mentally with your understanding of powers and exponents that you've been working with for your high school career. So let's do some without the calculator. Then as we move forward and get into it, we'll bring in the calculator. You can always use the calculator to check, but I just think it'll slow you down. I think you can actually do these without the calculator. So if you look at this first one, all right, which says solve y equals log base 4 of 64 equals y, I actually am going to rewrite it with the log or with the y on the other side. So literally just change to this. All right, it doesn't matter, right? I just like to swoop a certain direction. That's just how I practiced in high school and how I teach it. So if I swoop, it's 4 to some power y equals 64. So 4 to some power y, I don't know what it is, equals 64. So I'm trying to ask my brain, 4 to what power would give me 64? I know 4 to the second power is 16, and then 16 times another 4 is 64, so that means y is 3. All right, and again, this is asking for the exponent. So the exponent is 3. Okay, let's try this one. Again, I'm going to rewrite it. You don't have to. So log base 121 of 11 equals our answer y. Let's swoop 121 to some power equals 11. 121 to some power y equals 11. Now this one could be a little tricky. All right, I know that the square root of 121 is 11. All right, and what I've learned in my days in high school is that if you take the square root of something, you could rewrite that to be raised to the 1/2 power. So let me kind of show you that work to the side here. What my brain knows, right, is that the square root of 121 is 11, and you can always rewrite anything that's a square root as raised to the 1/2 power. So in order to make this true, I need that power of y. I need it to be equal to 1/2. All right, let's try this one. So we have log base 3 of 1/27 equals y. Let's swoop it. So we have 3 to some power y equals 1/27. 3 to some power y equals 1/27. This one can be tricky as well. The way I teach it is I always teach students, okay, 3, let me kind of show you my brain here. 3 to what power would give you 27? And hopefully you know 3 times 3 times 3, or 3 to the third power is 27. But if you look at the problem, it's not 27. It says 1 over 27. So to move it to the bottom, your power is not going to be 3, right? Your answer is not 3. It's going to be -3. That will move that 27 to the denominator, right? If you think back, use a different color, right? 3 to the -3rd power is the same as, so this is from your days in algebra, would be 1 over 3 to the +3rd power, which would be 1/27. All right, so hopefully that helps your brain kind of do that one. Let's try this one. So we have log base 2 of 1/32 equals y. Let's swoop it. So 2 to some power y equals 1 over 32. Now this feels very similar to the one we just did. So does your brain know 2 to what power, I'll use a question mark, would give you 32 in the numerator? And that question mark would be 5. 2 times 2 times 2 times 2 times 2, so 5 of them would give you 32. All right, but again, because it's not 32 in the numerator, it's 32 in the denominator, my answer needs to be a power of -5. All right, so that's how I do those without a calculator. Okay, now I mentioned this earlier in the problems when it came up, but anytime you have a base 10 for your logarithm, this is what we call the common logarithm. All right, so from here on out, if you have a base of 10, you don't need to write that base. It's not wrong. I'm not going to count it wrong, but again, it's kind of like writing that 1 in front of your variable x. Like no one does that. We just know that it's 1. So we call a base 10 logarithm a common logarithm. Okay, so let's go ahead and try to do these without a calculator. So again, I'm going to rewrite it. The log of 1,000 equals y. Again, I didn't write the base, but you know that there is a base 10 right there. So 10, all right, we're swooping around, 10 to some power y equals 1,000. 10 to some power y equals 1,000. All right, so you can actually do this if you know like 10 squared is 100, so 10 cubed is 1,000. Or what you probably have found out, or you're about to find out right now, is you can count the number of zeros. So there are 3 zeros in 1,000. So that power that it needs to be raised to is 3. All right, let's do it one more with that base 10. Well, not one more, but one more without a calculator. So log base 10 of 1,000,000 equals some value y. All right, so again, if you need to think of, that's a 10 in the base. So 10 raised to some power gives you 1,000,000. If you count those zeros, you'll see that you have 6 of them. So 10 to the 6th power gives you 1,000,000. Okay, let's use that calculator. Let me show you a couple things on the calculator now. All right. So if I want to do the log, let me rewrite it like this. So log of 123 equals some exponent, some value. All right, I can go to Desmos. And you'll notice that this base isn't written. So because the base is not written, we know that the base is 10, right? It's our common logarithm. So I'm going to go ahead and you can literally just type in the letters log of 123. All right. So again, if you would like to use a base that's not 10, you'll have to click the functions. And let's see where it is. I know somewhere. Might be, here we go. It's under calculus. Let's see if it's under something else. No, it's under calculus, but it's not. Don't worry, you're not doing calculus right now. But if you click that, all right, let me get this out of here. Right, if you wanted to type in that base of 10, you'd have to then type the base. There we go, 10 of 123. Again, you get the same thing as I mentioned of just typing the log of 123 because the base is assumed to be 10 if you don't write a base. But if you wanted to type something in that did not have a base of 10, you would need to go to functions, right? Go to this functions right here and scroll down to calculus till you see that log with the base that you would type in. Okay? It says 4 decimal places, so I'm going to write 2.0899 approximately. So y is approximately 2.0899. Okay, let's talk about the natural logarithm. So you've got the common logarithm, which is a base of 10. So I'll write that down here. So where did that go? Common logarithm, right? It's base 10 logarithm. For the natural logarithm, this is the base e logarithms, okay? So that number e is coming back into play. Again, you don't really need to know a ton about letter e, just besides the fact that it is a number that was discovered by Leonhard Euler, a Swiss mathematician in the 18th century. So it has a lot of applications in upper level mathematics. So I need you to get comfortable using this stuff we do in pre-calculus with a base of e. So if you see ln, all right, so that's not a 1, that's ln, and that's going to stand for the natural logarithm. So you've got log, all right, if you don't write a base, that's the common logarithm, and this ln is going to be the natural logarithm. Now, the nice thing about the natural logarithm is that it always has the same base. The base is always going to be e. We never write it, but the base will always be e. So if you have a base that's not e, you should not be using the natural logarithm. You should be using this logarithm, okay? So again, everything is the same, even if you're using the natural logarithm. So this is the natural logarithm of 500 is equal to some value. Let's type that in. Again, because you have that ln in front for natural log, all right, you just get to type in ln of 500 into Desmos. That's all you got to do. Just type in the letter L, the letter N, and then of 500, okay? So this is e to some power gives you 500. So e to the 6 point, let me show you, e raised to this power is going to give me 500. That's what we're saying. E raised to that power gives me 500. And again, you notice it's not exactly 500 because I technically am rounding, but 499 and 0.9 repeating is essentially 500. So 6.2146. 6.2146. Remember the idea being that if I think of this as e to some power gives me 500, e to some power gives me 500, and what is that power? It's approximately 6.2146. Let's do this one. I'll type it in the calculator, but I think you already might know the answer. As we mentioned earlier, all right, if you wanted to swoop this, I'll write it down. So the natural log of negative 500 is equal to something. You just use a question mark or a variable, whatever you want. So this is e to some power gives you negative 500. E to some power, I'll use a question mark since I use it there, equals negative 500. And I already mentioned, no matter what your base is, whether it's 2, whether it's 10, whether it's e, you're never going to be able to get a negative on that side of the equal sign. So I'm going to write undefined for the answer here. All right, but if you go ahead and if we show you by typing into Desmos, you would see that this is going to be undefined. So the natural log of negative 500. The natural log of negative 500. So you'll notice it says undefined. Not surprising. We know that, and if you need me to put it in parentheses, I can. These are the same thing, that we know that the natural log, or a log of any negative number, is not going to exist. So that's why we write undefined. Okay, now these last ones, just more practice. I'll go pretty quick here. If you're having any issues, come see me about them. Obviously, you're going to practice a ton in class. But when I do this one, all right, so this is 3 to some power equals 127. I think we actually already did this one. If it helps, I always write equals a question mark, and I know I'm solving for the exponent. So 3 to the third power would be 27, but because it's in the denominator, my answer is going to be negative 3. All right, let's see this one. 6 to some power gives me the square root of 6, so 6 to some power equals the square root of 6. And like I mentioned in an earlier one, when I see the square root of number, square root of anything, you could think of that anything raised to the 1/2 power. So if you write it like this, is 6 to the 1/2 power. So the answer is going to be 1/2. Let's try this one. Interesting. I'm just going to focus on this right now. All right, so this is 2 to some power gives me 1/8, and then I'll do the add 4. 2 to the third power is 8, but because it's in the denominator, that's going to be negative 3, and then bring down that plus 4, which gives you 1. Again, this is 6 times a logarithm. Let's just do this one. So 8 to some power gives me 4. This one is interesting. The way I'm going to do it is I'm going to think of, if I take the cube root of 8, the cube root of 8 is 2, but then to get that 2 to become a 4, I have to square it. So that's like 8 to the 2/3 power. All right, if that was like, whoa, how do you do that? Fair enough. Let's try it this way. Let's rewrite 8 with a base of 2. So 2 to the third power is 8. And if I write 4 with a base of 2, that's 2 squared. Think of back to your rules. This is power to a power. We're going to multiply. So 2 to the 3 times question mark equals 2 squared. When my bases are the same, these have to be equal to each other. So essentially that becomes 3 times something equals 2. And so if I divide both sides by 3, I get 2/3, which is how I got that 2/3. Now that's not the answer, right? Because now I need to do 6 times 2/3, which is going to be 4. Okay, let's try this one. 10, right? There's no base there, so this is a base of 10. 10 to some power gives me, let's see what this 10 to some power gives me 0.001. Now I'm going to write this as a fraction. It's always easier for me to rewrite this as a fraction. That's tenths, hundredths, thousandths, so 1/1000. And so my answer here, if I count the number of zeros, there are 3 zeros in 1,000, but because it's in the denominator, I need to put negative in front of it, so negative 3. The log of 1, we didn't really talk about this one yet, but I'll go and swoop it for you. So this is a base of 10. So 10 to some power gives you 1. Hopefully you think back to your days in algebra. Anything to the 0 power is 1. So whenever you see a log of any base and the argument is 1, it will be 0. Bring down the plus 7 to give you 7. Focus on this log first before you multiply by that 2. So I have a base of 10. So 10 to some power gives me 100 to the negative third power. Let's use something we did in the one of the previous problems. Leave this alone. Rewrite 100 as 10 squared. Right? 10 squared is 100. Remember what we did earlier. This is a power raised to a power, so you multiply. So that's going to be 10 to the 2 times negative 3 power, which is the negative 6 power. So this has to be negative 6. But again, I'm not done because I need to bring down that 2 times negative 6, which gives me negative 12. I know I'm going fast. Some of this is pretty tricky. So please come find me if you have any questions. Oh, a natural log. Base of e. So again, I'm just focused on this right now. So e to some power equals e to the 2/5 power. Now, what we talked about in previous problems is that when the bases are the same, the exponents must be equal to each other. So this question mark is equal to 2/5. All right, but again, that's not the answer. I need to do 25 times 2/5, which is going to be 10. All right, okay, so that's it for this lesson. Make sure you take some time to do the practice and come see me if you have any concerns. Good luck.